Hello, welcome back to my YouTube channel. My name is Joseph, and in this video, we are going to be explaining how we have fully implemented our project of the 110 noise recognition system, which we've been all along talking about theoretically. So in this video, we're explaining how we are implementing it. So let's start straight away. First of all, I'll talk about heat maps. Now, heat maps is a matrix representation of variables, which is colored based on the intensity of the value, and hence provides an excellent visual tool for comparing various entities. Now, I'll compare it to something like a histogram. Now, if known a histogram, it has bars. So the height of the bars gives you the extent to which a certain quantity is, whether it's very high or very low, so its height. So now for the heat map, it's like a matrix, but you're using colors in the positions where you would have put figures. So now the intensity or sharpness of the color will give you an extent to which the value is either high or very low. So basically, heat maps can be done based on numerical data. Now, for this project, we are dealing with images, and so we are unable to come up with a heat map for this case. Then coming up to correlation matrix. The correlation matrix is also a table containing correlation coefficient between variables, with each cell representing the correlation between any two variables. Now, it depicts correlation between all possible pairs of values and is a powerful tool to summarize a large data set and identify and visualize patterns. Of course, it's the same case as before. Our data set is made up of entire images, so there's no coming up with a correlation matrix. Next, I'll talk about box plot. Now, a box plot is a graph drawn to display a summary of the set of data values, having properties like min-mam, the first quartile, the median, third quartile, and also the maximum. Now, it can tell you about outliers and details more about outliers. We're going to see them in the next slide in the presentation. Now, it can give you details about your outliers and their values. It can also tell you if your data is symmetrical, how tightly your data is grouped, and if your data is skewed. Of course, it's the same scenario as before I already told you. Our data set is purely non-numerical, so we cannot come up with a box plot. Now, moving on to the next slide, I'll talk about feature independence plot. Now, feature independence plot, we've chosen to pick up at least one instance in our test data set, so we can plot and represent. So that's the first part, and the code you're seeing up there was written in a notebook, and that's how it's being implemented. And that's what you're seeing Valentine represents our feature independence plot. Now, I'll talk about also outlier plots. Now, first of all, I'll let you know what's an outlier. Now, outlier. Now, outliers are extreme values that differ from most other data points in the dataset. The simplest way to detect an outlier is by graphing the features or data points. Now, scatter plots and box plots, as already talked about earlier, are the most preferred visualization tools to detect outliers. Now, for this project, we didn't load these plots simply because they require numerical dataset, which we don't have. Now, shall try also to talk about illustrational patterns of interest. Now, for our dataset, still we are using some sample images in our test dataset. So we are going to be basing on what we call contours. So these green boxes surrounding each of these 110 characters, there will be our patterns of interest for this project. Now, for the illustration of trends in time and space, this shall be explored later in this presentation. Just keep on watching. Now, from this slide and the rest, these are simply sniped. We use the sniping tool of your Windows operating system to take up such images from our Jupyter notebooks. And so I'm explaining the whole of the code that was used to implement this. So it starts with the heading of 110 noise recognition system. Of course, now below are the various packages, libraries, and modules that we're going to be using in this project. I'll move on to the next slide. Now, at this point, we are importing our dataset. Now, our dataset was downloaded from Cargo, and this is how we are. Okay, when we downloaded it, it was already divided into 3 folders. That is, the train folder. Of course, now that one contained images we are going to use to train our model. Then there was also validation for the purposes of validation and also the test. So at this point, we are importing it. So now we are defining a variable called dir, that's dir, and we are into this variable we are storing the file path to our folder containing our training dataset. So that's why it ends with train looking video images. So the rest of the code we are storing, actually we are going to iterate through all the images in this train folder, and then we store them in a list called train data, as you can see it there. And then the other thing is we are going to concatenate like 2 images in each, so that we can be able to obtain what we call a feature and a label. So that's why the code is here being explained. And also we are using the OpenCV library to be able to implement these values. Now, details of the code can be explored at this point. So you can feel free to pause the video and look at it. I'll move on to the next. At this point, we're also importing the validation set. You can see that one was from the train folder. Was for this validation, you're getting from the validation folder. And simply, basically, we are doing the same process as before. Now, at this point, we just want to visualize how many images have been stored into the various lists. Now, for this validation, we are storing it in a list called VAL underscore data, as you can see it. We are doing the same process as before. Now, moving on to the next slide, I'll talk about the shuffling. So after we've got our images for the validation and the test, and we've stored them in the various lists, we are doing the process of shuffling. Shuffling just means basically mixing them up so that the process of training, there will be no such issues while the data was biased. So we're trying to mix them up so the model can be able to recognize them and the various ways in which they're presented to it. Move on to the next slide. Now, we are going to split our train data and also our validation data into the X and Y trains. So now for our train data, we are creating two separate lists called train X and train Y, of which now train X will be able to hold our features, while the train Y will be able to hold our labels. Just in the very ways, if you're plotting, let's say a graph, you'll have an X and a Y value. So And our project, remember, is a classification problem, so that's why we have to split them. Remember, this was because of the join that we did earlier, concatenating the two using the join method in order to get one image and the other. So that one is a feature and one is a label. Now it's the same process we are doing for the validation. We are creating two separate lists, VLX and then val_y. So each of them stores features and labels appropriately, as you can see. So now the next process is binarization. This is the process of converting our labels into binary digits. So we are using the label binarizer. So at this point, you can see we are actually converting our labels. That is the ones that have the Y. The labels are the ones to which you are mapping, or where we are classifying our input data. So input something and classify it into a label. So we are converting them to binary digits, as you can see. Now the next part is converting our data set to a NumPy array. Now I'll let you know that in machine learning, Python uses image data in the format of height, width, and channel format. And of course, these images must be converted into what we call a NumPy array because, as you know, our machines usually deal with numbers. So to convert them to, when you convert it to a NumPy array, there will be figures between 0 and 255. So after converting them into that, we shall have to follow the process of normalization, whereby we convert them to values between 0 and 1. That's simply by dividing by 255. And this will be seen in the next slide as we implement it. So you can see here, we are doing it for the train, for this list called train X and also train Y. Of course, now for train X, we convert it to NumPy array by np.array, then divide by 255 to convert it between those values I talked about. So this will be able to normalize our data. That's actually for the features, not for the labels. That's why you see it's not, but for all the labels and also the features, we convert them to NumPy array. So it's being implemented for both the train data and also the validation data. Now here, just below, as you can see, we are just trying to analyze the shape. That's the dimensionality of our data sets, and it's being depicted as you can see. Next, we are going to be creating our model and also doing the process of hyperparameter tuning. Now, I'll let you know about what we call hyperparameters. Now, hyperparameters are variables which determine the network structure and variables which determine how the network is trained. Now, for our model, what we are considering for hyperparameters, this shall be the number of neurons in each of the hidden layers, and then the activation function, the optimizer, learning rate, batch size, and epochs. This will be seen as we proceed to the next slides. So for our model, we are using a sequential model. As you know, there are several models for the convolutional neural network. For example, the functional bus parameters, we are using a sequential model. And then we are creating the various layers of the CNN model, the hidden layers. So you can see the model.r, then we add the com2d, and then we pass in specific variables, the padding, the activation, as you can see. So we are specifying the activation function be the real one, and then we pass in all the other variables. So if you can analyze this code, you see that we shall have 3 layers in the hidden layer. Yeah, so, and then we do the flattening. So next we actually print out a summary of our model. So this can be analyzed here below. Feel free also again to pause the video and analyze it if you can. Then next I'll talk about the model compilation. So the model compilation, we have to pass in the loss, the loss function, the one you shall use to get the loss for the train and also for the validation. In this case, you are passing a variable, we're going to use the categorical cross entropy. Then the optimizer is setting it to Adam. Then metric, our evaluation metric shall be the accuracy. Then model training, as you know. Now, model training, we use the function model.fit. Then we pass in our variables. The two separate lists, train X and train Y, that's for the train data set. Then we set the number of epochs to PPT, then the batch size 32, validation data, and also passed in, as you can see, validation, VLX, that list, and also this list that is holding our information. Of course, remember, we already converted them into NumPy arrays. Then we set also the variables to 1. So as you can see, the code ran in the notebook, and then after running, it was successful, as you can see. So now we ran up to 50 epochs, which was successful. So now this is just an independent plot, as you can see. It's a plot, the process during the process of training, there was training and validation, both were going on. So we are training, actually we are plotting accuracy against the number of epochs. So as the epochs were increasing, also the accuracy was increasing. Accuracy levels were almost constant, so you can see it. And also we have another plot for the training loss and versus validation loss. So you can see them, whereby the blue line represents for the train and also the brown one for the validation. So you can see them, can visualize them. Then the next process is for evaluation of our model. Now, evaluation, according to our lecture, we are told we must pass in. We evaluate based on the validation set. So that's why you're seeing model evaluate, and you're passing the validation list for the X and also for the Y. Of course, now model evaluate returns the loss and also the accuracy. So now these losses, those figures you're seeing which have been returned after the evaluation has run. 1 is for the loss, that is 0.18. That's approximately 1% or 2%, something of the sort. And then for the 99.2 or 0.3, that's for the accuracy for the validation set. Now, move on to talk about for the recognition process. Now, the rest of the code here, we're just trying to see whether our model can actually do the prediction. That's the pre-processing, as you can see. So we have 3 methods. Depth contours, which tries to look at the contours and then be able to identify the words. Of course, now we're trying to move from right to the left while identifying each of the characters. Then the get letters, this one now is a method that fetches the list of letters, and then the get word function gets the individual words. So this code is implemented. Feel free to pause the video again, and then you can analyze through. Now, my interest is I want to take you through at the point where we're passing some words. Now, we're passing in a file path, which is leading to an image. in our test set. So this image is this one is you're seeing JORIS, which we've actually plotted using the matplotlib I'm sure function. So the mode is able to recognize some of the words and print them. Of course, the recognition is not yet 100% perfect, but you can see it tries to recognize, combines JOR into W, then the R is maintained. Now, let me show you also some of the other recognized. Now, there is another one called Caroline, as you can see, those ones that have the green boxes around them. So those are the images in our test sets, but they're being recognized as you can see. And then this forms our actual work. Actually, so this is the recognition as you can see. Now, the best recognized of all is this word Valentine, as you can see to the right. Valentine was recognized, only the letter E was misinterpreted as F. So this work is still good to be corrected and improved later. Thanks very much for watching. Meet in the future videos.